All right, so now in this video, we're going to talk about the selection rules for absorption of many electron atoms. So these look a heck of a lot like the absorption selection rules for the hydrogen atom, with a couple of small exceptions that I'll draw a lot of attention to. So the first such rule is going to be that the change in overall angular momentum is plus or minus 1. And now the big change relative to the single hydrogen atom is that delta L can also be 0, but there is an exception. So this is not allowed if L is equal to 0. So L equals 0 to L equals 0 is not allowed. Okay, we're going to see another example of that. And we'll talk more about how to interpret this in a second. Delta S is also equal to 0, so you can be no change in the spin. Delta J can be 0 or plus or minus 1, but this has the same exception, so except that 0 to 0 is forbidden. And there's one tiny little addition to it. It's kind of a clarification on what is meant by this delta L suddenly being allowed to be 0 here. And we're going to write that as delta L, or small l, is equal to plus or minus 1. Okay, and so the idea here is that there needs to be some electron somewhere in your atom that does change angular momentum. And often this means that the overall angular momentum for the atom can change, but it doesn't have to, right? Because we have sort of a complicated combination of angular momenta. It is possible that when you combine all of this, the overall orbital angular momentum doesn't change, but still the orbital angular momentum for at least one electron does need to change. So the place where this comes up most is that if you have a really simple configuration, like let's say you have something like sodium where you have 1s1, sorry, 1s2, 2s2, 2p6, right? So relatively simple closed configuration. And then you have something like 3s1, or the same thing and 3p1, or the same thing and 4d1, right? So in this case, you have basically a core, and then you have this outer valence electron that is doing all of the actual motion here. And so in this case, the little l here is just going to correspond to the angular momentum of this valence electron that's hanging out here. And so here what this is telling you is that if you have a situation like this, where you just have this like one lonely little valence electron that's going to do all of the motion, then this thing needs to change by plus or minus 1. Okay, so in the configuration, then this delta L needs to change by plus or minus 1. Okay, so let's go through a little bit of an example, and we're just going to label some possible transition in the sodium atom, and try to figure out which ones should be allowed. All right, so I've made a quick little diagram where we're collecting a bunch of different states according to their term symbol. So everything in this column has the same term symbol. And then we're just labeling the sort of last electron orbital that would be in the sodium configuration. All right, so this is going to be just a quick way to sort of write down all the different possible term symbols, but also the different electrons that this could correspond to. And what I'm going to do is just write out all the different transitions that would be visible according to these selection rules. So remember, the delta L for little l needs to be plus or minus 1. That's going to be the biggest one. All of these have the same S value, so this isn't going to come up. And then the other one that's going to be really important to pay attention to is the delta J and the delta L. Okay, so we just sort of start, and I'm just going to draw what's allowed and try to comment as I'm doing it. So you can have 3p, so the 3s can go to either of the 3p or the 4p states. There's really no restriction there, right? Because the 3s has the s 1/2, and both of the p's are allowed based on delta j, and delta L is equal to 1, and so that part are both allowed. Next, if we're starting from 3p, we can of course go up to 4s, but we're going to keep going to the right. So the p1 half over here can go to the d3 halves, but it can't go to the d5 halves because that would correspond to delta j equals 2. Right, so these transitions are allowed. And all of the transitions starting from p3 halves to a d level are allowed because all of those would correspond to delta j equals 1 or 0. Right, so all of those lines are allowed. And then also we can have transitions that go from 3p to 4s because that gives a delta L of 1, and from 3p to 4s for p equals 1 half as well. So those are both separately allowed. But what I want to really emphasize is that, right, so the transition from 3s to 3d is not allowed because that would correspond to delta L equals 2 for big L and also for little l. But also the s to s is not allowed because that corresponds to delta j equals 0 and also the delta L equals 0. But also the 3p to 4p should not be allowed because that would break this small l, right? So the sort of the valence L is not changing by 1. And so that means that this transition is not allowed for this particular case. Okay, and so with that, we can see all of the selection rules, and we know how we could assign all of the possible transitions in even something as complicated as the sodium atom. Now, what's nice is there are lookup tables where you can find all of these energy levels and sort of reconstruct what the different transition energies ought to be.